Carl Friedrich Gauss, born in 1777, was a prodigy from a humble background in Germany. Stories abound of his childhood genius. At 7, he astounded his schoolteacher by summing numbers from 1 to 100 in seconds. His method revealed an early aptitude for pattern recognition. The Duke of Brunswick became his patron. This support allowed Gauss to attend university, where his genius blossomed. As a teenager, he proved the constructability of the regular heptadecagon. Gauss's interests extended to astronomy. His method of least squares became indispensable in various fields. His meticulous nature earned him the nickname Princeps Mathematicorum. The construction of regular polygons, using only a compass and straight edge, had fascinated mathematicians since ancient Greece. For centuries, it was believed that only certain polygons with specific numbers of sides could be constructed in this way. Gauss, however, shattered this belief with his groundbreaking discovery concerning the heptadecagon. At the tender age of 19, Gauss proved that a regular polygon with 17 sides could be constructed using only the classical tools of compass and straight edge. This was a feat that had eluded mathematicians for millennia. The elegance of his solution lay not only in the result itself, but also in the novel algebraic techniques he employed. This discovery was not merely a geometrical curiosity, it had profound implications for the burgeoning field of abstract algebra. Gauss's work demonstrated that the seemingly abstract world of algebraic equations could have tangible geometric interpretations. This insight paved the way for further explorations into the interplay between algebra and geometry. The achievement of constructing the heptadecagon was a testament to Gauss's exceptional mathematical prowess. It also served as a harbinger of the groundbreaking work he would continue to produce throughout his illustrious career. His ability to connect seemingly disparate areas of mathematics, such as geometry and algebra, would become a hallmark of his genius. Gauss held a deep fascination with number theory, a branch of mathematics dealing with the properties of integers. He considered it the queen of mathematics, and his contributions to this field were profound and far-reaching. One of his most celebrated achievements was the proof of the law of quadratic reciprocity. This law, which had been a subject of much speculation and partial proofs, establishes a relationship between the solvability of certain quadratic equations. Gauss, with his characteristic thoroughness, provided the first complete and rigorous proof of this fundamental theorem. The elegance and ingenuity of his proof cemented its place as a cornerstone of number theory. Beyond the law of quadratic reciprocity, Gauss made numerous other contributions to number theory. He introduced the concept of modular arithmetic, a system of arithmetic for integers where numbers wrap around upon reaching a certain modulus. This concept, seemingly abstract, found practical applications in cryptography and computer science. Gauss's fascination with numbers extended to their distribution. He investigated prime numbers, those elusive building blocks of integers, and developed a conjecture about their distribution. Though he was unable to prove it during his lifetime, his conjecture, known as the prime number theorem, provided a significant insight into the seemingly random nature of prime numbers. The eventual proof of this theorem, decades after Gauss's death, stands as a testament to his enduring legacy in number theory. While renowned for his work in algebra and number theory, Gauss's contributions to geometry were equally profound. He revolutionized the field with his development of differential geometry, a branch of mathematics that studies curves and surfaces using calculus. His work laid the foundation for our modern understanding of curved space. Gauss's most celebrated contribution to differential geometry is his Theorema Egregium, or remarkable theorem. This theorem establishes a fundamental relationship between the curvature of a surface and the angles of triangles drawn on it. It demonstrated that curvature is an intrinsic property of a surface, independent of how the surface is embedded in a higher dimensional space. This groundbreaking insight had far-reaching consequences, particularly for physics. Albert Einstein, decades later, would draw upon Gauss's work on differential geometry to formulate his general theory of relativity. Einstein's theory, which describes gravity as a curvature of space-time, owes a great debt to Gauss's pioneering work on the geometry of curved surfaces. Gauss's contributions to geometry were not confined to theoretical realms. He was also actively involved in geodesy, the science of measuring and representing the Earth. He developed new techniques for surveying and map-making, which were instrumental in improving the accuracy of maps and navigation.